Hello everyone, my name is Naveed Anwar from AIT. As I mentioned when we started this series that we are going to talk about the building blocks of structural engineering, and I think nothing is more important than structural modeling because it gives us the tools to create a representation of the real structure in a computer simulation. And when we do the analysis, actually we are always doing the analysis of the model of a structure and not the structure itself. So that is why it is critical that we create a model which represents the real structures and its response as closely as possible. It will be almost impossible to fully create the real structure in a model. There will always be some assumption, there will always be some things that we cannot capture. But as a structural engineer, our job is to make sure that we model enough so we can get the response that we need for the purpose that we are doing the analysis for. And this modeling is a very wide subject because it ranges from so many types of elements that can be used, so many types of software that can be used, so much detail of the modeling that we can do. But today I will just focus on a very simple structure and try to highlight some of the key issues and key challenges that we have in structural modeling. So this structure is basically just a simple beam resting on a masonry wall. You can imagine that this appears to be a very simple structure and should be easy to model and analyze. But we will find today that even for a structure as simple as this one, it becomes very difficult to do the modeling if we want to capture all of the response or all of the practical and realistic behavior that can occur. This will lead us to the modeling challenges that can occur in bridges and then later in buildings and other structures. So let's look at just a beam resting on a wall and see what it can tell us. Basically, we need two things to do this. First of all, we need a way to represent the structures mathematically properly. That means we need a model of a structure which is realistic in terms of the structure that we are trying to analyze. And the second is that we need tools and methodologies that can help to solve this structure, give us the response that we're looking for. So we want the right model for the right response, for the right excitations, and that is the problem we are trying to solve. And we need a model which can represent the geometry, which can represent the materials, which can represent the excitation, which can represent the invisible behavior also within the structure that we cannot see. So all of that is needed. So let's see how can we do this and what are the other challenges. Now, like I said, I'm taking a step back. I'm not taking a very complicated example today. I'm going to start with a very, very simple example of a structure. Just a beam resting on two walls. Nothing can be simpler than that, right? And if we can model this properly, we should be able to move forward. You might say you don't need analysis or modeling to determine the response of this structure. I can do it by hand, by WL squared by 8 or WL by 2 or something like that. Completely true. We don't need a computer modeling to solve this problem. But let's see if we had to model this structure completely and properly, what will be the challenges? So first of all, we would like to model this structure realistically and calculate its behavior for different excitations, not just for vertical load. So let's see what are we talking about in that context. So basically, we would like to represent the materials realistically. Now, this is a reinforced concrete beam. We have rebars in there. We have the two different materials putting together. We have a masonry wall there, which is made of brick blocks, which has mortar in there and so on. We have supporting system, foundations. So can we model all of those materials realistically? Can we represent the geometry correctly, realistically? That means it captures the behavior. Can we represent the connectivity between these elements? How is the beam resting on the walls? What is that connection? Is it pin? Is it roller? Is it spring? What is it? How do we represent that simple connection where the beam is simply resting on the top of the wall? How do we capture the invisible behavior? For example, friction between the wall and the beam, or the sliding of the beam, or falling off of the beam. right? How do we do that? And then how do we understand the response that we will compute and make some decisions that are useful? So let's get into it. Let's see, number one, the simplest case. In the case where we have a vertical load on the beam, and how do we calculate the response for a vertical load? And that is obviously the simplest case. And then what anybody will do is that they will take this beam and they will put it on a roller and a pin support. Probably they will model it like that, apply the vertical load, and then easily calculate the bending moments and even deflections and shear forces and all. There is doesn't seem to be any problem with that. But look at the first problem. When you model it, you model the center line of the beam, which is actually far from the real support of the beam. It's not the same location where the beam is in contact with the wall. So you're modeling a beam center line which is away already from the real support, and that will start creating the problem in our modeling. But okay, let's forget that for a minute, and we can do this model and we can get the response for the vertical load. So we use the concrete modulus of plasticity. We use average models. We neglect the rebars. We just assume it's a concrete. And we use the initial elastic model or tangent elastic model, or do we use the secant elastic model? There are many options there. So we have to make a choice on which elastic model we will use even at this point. And then do we use gross cross section, or do we use the cracked section? Because when you apply the loading, the beam will crack, and then the cross section will change along the length. It will crack more in the middle, less close to support. So which cross-section properties should we use for calculating the response, the deflections, for example? Then let's say we use the line element or frame element to model this one, and like I said, we put it on two support, one roller and one pin. Which side should be pin and which side should be roller? Because in reality, both the supports are identical. The beam is just resting on the wall. So you are arbitrarily saying that one is pin and one is roller. Which one is which and why? So we'll come back to this again. And then, okay, then we apply a vertical load with a UDL. Again, whether it is applied at the top, at the bottom, of the center line, that's a question, but let's say we assume that it is applied at the center line. And then we can do a linear elastic analysis and we can get the response. It's a simple thing, but as you can see, we already raised many questions here. Let's go to another case, next step. Let's say that the load is not vertical. Let's say now that the load that we are talking about is actually a horizontal load or a horizontal displacement. For example, there's a load coming from this side because of any reason, maybe it's earthquake movement, or there is a temperature change, or there is a shrinkage in the beam, so it is causing deformation in the beam, axial shortening or expansion. Now what do? Will that model that we just made work? For one thing is that if we use the pin and a roller condition, then if we have a pin on this side, if you apply the horizontal load, that pin will absorb the load and it will not go to the other support. But we know very well that the load from this beam, horizontal load, should be shared by the two walls. How will that happen? How will we model that? So if you use pin here, roller here, then we already are in trouble. If we use both rollers, then we again are in trouble because the beam will simply slide off the walls and we will not get any reactions. What about when we have the thermal expansion? Then the beam is supposed to expand on both sides. What will it do to the wall? What kind of reactions will be induced? So will the walls provide enough restraint or will they not? So all these questions start to come up when we simply change the direction of the loading from vertical to horizontal. And now we cannot really model in a very simple manner without making several assumptions. Let's go one more step. And we say, okay, let's say the beam is like this one, we're looking from the side, and there's a wind blowing on that side, and actually it is trying to topple the beam. So there's a wind pressure coming from the side. Now we have a completely different problem to solve, because we need to see the centerline model that we made last time may not be relevant anymore, because first of all, the beam center line is here, support is here, so we have a gap in between. And also in reality, this beam might topple and overturn over the wall, But our center line beam model will never tell us that that can happen, because it is representing the beam at a center line which is supported on both sides, so it cannot topple, it cannot rotate in that way. Even it can rotate, it can only rotate about the center line, not about the top of the wall, which is far from the center line. So that means now our traditional simply supported roller pin model will not work in this case, right? And we need to go beyond that. Let's go further. So now you can see that there are several issues that have come up in this, but just because we change the loading. That means we cannot seem to use the same model for different loadings, which should not be the case. In an analysis program, when you make a model, you apply different loadings to the same model. And in our case, we can see that it will not be the case. Let's go further. Okay, let's say that we realize that a simple centerline beam on roller and pin support may not be sufficient. Then what options do we have? Let's say we go to a computer program, and we say, okay, I'm going to model that as a frame. So I'm going to represent the wall as a vertical column, and that wall also as a vertical column, and I'm going to represent the beam as a frame, and then I'm going to create this frame. But the first problem again is that the beam will be modeled at the center line, and walls will be ending here, so there's going to be a big gap between the center line of the beam and the supports where the beam is actually resting. And so we have this offset between the center line and the supports, which now will create a problem. Either we lower the beam down so that the center line comes to the top of the wall, or we raise the walls up to match with the center line. Both of them are incorrect because they alter the physics of the structure. That means our frame model now has some challenge. Obviously, there could be many ways to solve that. We'll come to that in a minute. But you can see that even creating a simple frame model for this example runs into trouble right away. Then let's go to another option, a frame shell model. Let's say if the wall is very long, we don't want to represent it by a column. We can create a shell model of the walls to make it more realistic. And when we can represent the beam as a frame, and then we try to connect them. But that does not solve our problem, because there is still this difference between the beam center line and the top of the wall. That gap is still there, and we need to do something about that. But this model will be slightly better for the walls, but it doesn't solve the problem for the beam, and especially doesn't solve the problem of the connection between the beams and the wall. Right? But at least now we know that we have an option of doing a simply supported single member, we have an option of doing a frame, we have an option of doing a frame and a shell. Then let's say we want to create a complete shell model. Another option is that we go one step further, and we say, okay, we will represent the wall, which is it's a planar structure, by a shell element. We will also represent the other wall by shell, and we also represent the beam as a shell, because beam has a depth, so we can model it as a shell. And now we have solved a few of the problems, because the first problem we solved is that the connection or the support of the beam is now actually on the top of the wall. So that gap problem or the geometric inconsistency has been resolved, and we can actually place the beam exactly where it is, and we can model the geometry reasonably. But several other problems we have not solved. We have not solved the problem of the gross cross-section of the materials, and so on. And we haven't solved the problem of the connection between the beam and the wall yet. But geometrically, the model has started to look better, right? And we can have a good physical sense of the structure. Now, let's go to next step. And we say, okay, let me model the whole thing as a solid. So that because in the previous model, if I go back, we still have a thin shell resting on the wall, and it doesn't have the stability on the transverse direction because of something called the orphan degree of freedom problem. When the degrees of freedom of one object do not match with the degrees of freedom of the other, so some degrees of freedom are orphaned, so the connection will not be fully established. So to solve that and to solve other problems, we could say that, okay, I'm going to model everything as a solid element. In fact, mechanical engineers normally always model their structures as solids, because they physically correctly represent everything. But in civil engineering, in structural engineering, we make normally a lot of assumptions and simplify the structures. So now we have a solid model. That means the wall is physically correct, the beam is physically correct, the beam is really sitting on the wall at the correct location, and the dimensions are now correctly modeled. If the beam is wide, it will be more stable. If the beam is narrow, it will be less stable, and so on. And same is the case with the walls. So geometrically, it's a very good model because the change of the cross-section will not change the results or will not change the assumptions, and it will just be correct. But the problem of the connection between the beam and the wall still not mentioned. And the other problem now we have created for ourselves now is that it is not easy to calculate the bending moment in the beam anymore, because the solid element will not give us the bending moment and shear as we normally get from a frame element. Now we only get stresses, and those stresses will have to be integrated, converted back into bending moments and so on, and those stresses are not useful for reinforcement design directly. We will have to do a lot of processing to get sense of what reinforcement we need. Also, it will be very difficult to induce cracking or incorporate some reduced stiffness into the solid model, because in a beam we can simply modify the properties by changing the property modifiers in shear and torsion and axial and bending independently of each other. There are 6 stiffnesses that we can modify to get the behavior that we want. In solid, we don't have that opportunity anymore. It's more or less complete. So even though we solved the problem of the geometry, we created problems now in the result interpretation, and we also created problems in the modeling of the properties or the modified properties. So while each model gets better in one direction, it gets worse in the other direction. And especially, we haven't solved the problem of the connection between the support and then, because if you just connect it, it will become rigid connection, and the results will be very different from what we really expect. So if you look at that in a SAP, for example, you could make different types of models for the same thing. This is a simple beam. I represent it in an extruded form. This is a beam, center line on wall, beam on shells, and then different models of shell on shell and full solid models. You can create them in SAP if you like. For if this simple structure, we can have several options and some disadvantages, and they can all handle some loading and cannot handle some loading. So none of the model is actually really solving the problem that we started with. And we started with a very simple problem of a beam on 2 walls. What can be simpler than that? So what we have learned so far is that even with that simple problem, it is very, very hard to model everything as we want, unless it's a thesis, master thesis, in which we are only doing this for 6 months or 1 year. But in a design, we have very little time to do that. So if you just look at the model, the way they will all have different response. Some will give you bending moments, some will give you stresses, and you can see solid models of different kind where we try to solve many problems of beam going to the end, not going to the end, and so on. And if you look at one parameter, the deflection in the beam, center of the beam in different models, you get different answers here from one to the other. Every model is giving you a different value of the deflection in the middle. And if you just use the manual calculation in the middle, some are higher, some are lower, and the variation is quite big. So the question is, which model is right? In this particular case, actually none of them is right, because in the deflection of reinforced concrete, we have to incorporate the cracking and the effective stiffness because of the reinforcement, and we have to incorporate the long-term loads, we have to incorporate the shrinkage, we have to incorporate creep, we have to incorporate so many other things that none of these models can handle so far, which means that even with all of this, we didn't get the deflection right. We might get some of the forces right, we didn't get the deflection right. We didn't solve the problem of the connection between the beam and the wall yet. We only have few options. Either it's a hinge, or it's a pin, or it's a roller, but the real connection is a sliding member resting on top of the wall. So how do we do that? So that brings us to some other problems that we actually did not solve. First of all, like I said, the beam can slide on the wall, and we didn't incorporate that in our modeling. Sliding, friction. The beam can actually fall off from the wall. Our models will never show us the beam falling down from the wall, no matter how much load we apply. The beam will always be resting, will be connected, unless we use really advanced modeling. Then the other problem is when the beam rotates, we assume that the beam is resting on the center line of the wall. But actually when it rotates on the edge of the wall, not on the center line. So that means the span that we assumed is also not correct. And then actually that rotation at the edge of the wall will change the reactions, not from here, but from the edge of the wall. So those things we just didn't capture because we assume that we are modeling the things at the center line and we have a pin roller at the center line. If the wall is very wide, this could be a big difference. Let's say the wall is half a meter on each side. So your span estimation will be off by half a meter. Deflection, moment, everything will be off by that. So many things, and some people will use clear span, some will use centerline span, but what is the real span we don't know. And then the stresses around the edge, the wall, could be very high around this area. So you can imagine that how it will go. And then this whole thing, this sliding here, we have not been able to capture that properly also. Then to solve these problems, we have what we call the behavior elements. So because we could not solve this problem by physical modeling, because no matter how fine we made the modeling, for example, we use the solid element, shell element, whichever, we still could not capture the behavior that we were trying to capture because so many things we couldn't model. And that's why these behavior elements come to our rescue. And behavior elements include constraints. Constraints could be used to model the offset between the beam top and we could use rigid links. We could use springs, links, dampers, isolators, hinges. Links are the most powerful of these elements. They could be linear, they could be non-linear. So by using links, we could model the friction between the wall and the beam. We could also model the non-linear falling off. By that, we could model lift, uplift, and we could model many things. So by using the appropriate links and other things here, we could actually model many of the things that we missed. So by combining a good physical model with good behavior elements, we could actually get close. But it's a lot of work for a problem as simple as that, and I'm quite sure nobody will actually spend that much time for a beam resting on walls. But let's go to the next important. So I hope, we actually plan to do more talks about use of these in a separate, because time is not enough, and each one of them requires an extensive discussion. So I hope we can continue presenting these things in future talks. So we have not done yet, because we ignored the materials, or we did not think about the materials in detail. We only look at the basic properties, but materials have many properties. So let's say materials that we are looking at, basically for analysis, we only need E, but we already are not sure which E we should use, because E keeps changing as the structure deforms or as the strain increases. The Poisson's ratio, shear modulus, thermal expansion coefficient, these are simple parameters that you could compute, even though they may be difficult to assess. I will come to that in a minute. And for design, we also have other properties like yield stress, yield strain, failure strain. We did not use them in the analysis yet. So that means some of the material properties that we have, we didn't really use them yet. And then some of the properties that we have here, we are not sure what values we should use. And then we have other properties that if the beam was pre-stressed concrete, we will also have to deal with relaxation. We'll have to deal with fatigue if there is repeated loading applied. We'll have to deal with creep if it's concrete, with shrinkage, and with confinement if we had reinforcement which is confining the concrete. So we will have to deal with these things and incorporate these into the material properties. So the basic material properties, everything, even the concrete strength will change because of the confinement, right? The stress strain curve will change because of that. So which means that now we have basic material definitions have so many things to consider. And all of these, or many of these, are actually dependent on some other things. So basic material composition will govern the properties. Of course, it's concrete, how many type, which type of concrete, aggregate, and so on. initial conditions will govern whether it was cast, whether it was lifted, whether it was cast in place. How was it made? That will affect the pre-strains or pre-stresses in the member. State of strain, whether the beam has been pre-strained, it has expanded before, it was contracted before, what time of day, or what day it was when it was cast, was summer or winter, morning or evening. So that will affect the initial conditions of the structure. Direction of strain, which direction the strain was applied before, that will affect the properties. Then the history of strain, how many times the strain was applied and removed from the current date. So what is the history? That will affect the material properties today. So a new beam is not the same as a beam which has been in service for 20 years. They will have different properties. Then time since initial strain. As you know, concrete gains strength over time, but some things like creep and shrinkage also go the other way. So that will have to be taken into account. Temperature will have to be taken into account. Whether it's summer or winter or it's elevated temperatures during fire, properties will change, right? Cyclic strain. So if it is a cyclic load applied, degradation would have occurred. How will we incorporate that into the current analysis? Rate of strain, velocity and acceleration will change, frequency will change. So just the properties, not only that we have so many properties, we also have the properties which depend on so many other considerations. So picking one property out of that is all we are doing. We are picking one instance of the property. For example, when we say this is my modulus of elasticity, we are picking that modulus of elasticity at given time, at given temperature, at given strain, at given history, at given everything. And it is not the same. It depends on so many other things. So that means our analysis is only specific to a particular instance of the time that we took those properties from, right? So these are the things that we have to also consider when we do the modeling and analysis. Then just look at the wall itself. We haven't even talked about the wall itself. Let's say it's a masonry wall. Then each block is a separate unit. They are connected by mortar. So we normally, when we model shell element or solid element, we assume that to be homogeneous material, but it is not. Every block is an independent block connected by mortar, and the mortar can break, we can have cracks there, and if we just do one modeling of the wall, it will take a lot of time if you use Abacus and other programs to be able to get this kind of response. It actually requires a considerable effort. Normally it can't be done for the whole structure, only we can do one wall at a time. I remember at one time we had a software called Strand, and somebody purchased it, and at that time it was the most advanced, it still is, very good software for finite element analysis. And one of the user, he was a researcher in the university, he said that this Strand cannot run his problem. It's too big. And I said, what are you trying to analyze? And he said, I'm trying to analyze a wall which is 3 meter by 3 meter. And I said, how can a wall at 3 meter by 3 meter consume the entire software capacity? Because he was modeling a block of wall with with holes inside and keys. And he was modeling it by using thousands of such solid elements, and each block connected to other solid element by links. So he used a couple of million elements to model a wall 3 meter by 3 meter. And if you go to that level, obviously you can't replicate on a big structure. So we have the capability to do that, but it's not a useful analysis that we can do. Now, you might be wondering why we are talking about a wall and a beam. We were supposed to talk about bridges and buildings. So let's get back to our topic. How does it apply to bridge modeling? So if you look at a bridge now, a simple bridge, on the right-hand side, it is basically beam girders rested on a pier, which is quite similar to the problem that we started with. So all the problems that we faced in a beam resting on walls are actually applicable to a bridge girder resting on pier. It's the same problem, even more complicated than that, because we have bearings and other things coming up. So the point I'm trying to make is that when you look at a bridge structure and you look at a girder and your pier, you actually have to address most of the problems that I just indicated on the first example. So we can learn from that example, and we can then apply it to a bridge model that I showed here. And then you can actually create a very detailed model. If this is a simple bridge with one pier and two foundations and a couple of beams, we can create a model which is made from all shell elements here, solid elements over there, and these are the nonlinear links that I was talking about to model the connection between the girder and so the girder is sitting on that, so you can model that connection by nonlinear links, by gap elements, by friction elements, whatever you want. And you can have different properties on the two directions. You can model the pile cap here by using the strut and tie model. Dr. Dhamika actually did his work on exactly this problem, how to convert a solid element mesh into a strut and tie model. So he spent a year working on this particular issue. And you can also model the piles and then you can put springs everywhere. So you can go on from the top to the bottom and try to model as much detail as you like from this one, and it can go on even further than this one. But my point is that you can have a simple girder sitting on pier up to a complete model of the entire bridge, deck, supports, pile caps, piles, and soil, all in one go, right? And anything in between. So that's what I wanted to touch upon on the modeling of the bridges, because it basically has all of the problems that I started with. The important thing to remember is that we should look at the purpose of modeling. As you can see, depending upon what do we want, we need different models. If only gravity load, maybe simple model. If horizontal and those loads, then it's different models. Modeling elements and analysis procedures should be selected appropriately. So we should pick the procedures that are right for the problem that we are trying to solve. Don't overkill it and don't underkill it. Even if we cannot model everything, we should be aware of the limitation. This is very important, this step. Even if we cannot model everything, which we cannot, at least we should know what did we miss and how that could have been incorporated or can be incorporated, or how that can be approximated, right? So this is very important, having to be aware of what we didn't model. Don't think that your model is complete. Your model is almost never complete. You will always miss something, but we should know what we missed and what impact it might have on the response. Is it acceptable or not?